Hello viewers, welcome to add-on. In this question, we are asked to derive the expression of the following: ripple factor of a half-wave rectifier and efficiency of a full-wave rectifier. Okay, so let us start with it. I'm just increasing it. Okay, so ripple factor for a half-wave rectifier. So the ripple factor of a half-wave rectifier, which is denoted by gamma, this is equals to I of AC divided by I of DC. Okay. And if we do the calculation, I of AC is equals to I of RMS square minus I of DC square. Okay. So I of AC, this is equals to I of RMS square minus I of DC square. So if we put the value of this I of AC here, we will be getting root over I of RMS square minus I of DC square divided by I of DC. Okay. So if we do the division, we will be getting I of RMS divided by I of DC whole square minus 1. Now, in order to find this ripple factor here, we need to find the value of this I of RMS and this I of DC. Okay. So, in order to find these values, we will have to do another calculation for a half-wave rectifier to find the RMS value and average value, or we can say the DC value of the half-wave rectified output. So in a half-wave rectifier, suppose the input waveform to the half-wave rectifier is like this. It has a positive half cycle and it has a negative half cycle as well. And we know for a sinusoidal waveform, the time period of the sinusoidal waveform varies from 0 to 2 pi. Okay. So this is 0 and this is 2 pi. And the middle here, this part, this is pi. Okay. And if we pass this output through a half-wave rectifier, we will either get the positive half or we will get the negative half. Okay. I am denoting it by different color because we don't get this two halves simultaneously at the same time. Either we will be getting the positive half or we will be getting the negative half. Okay. We don't get both the halves simultaneously at the same time. Okay. So the period is same. This period is also pi and this period is also pi. Okay. So we can say that the period varies from 0 to pi in a half-wave rectified output. So if you want to calculate the, we can say if you want to calculate the average value of it, if you want to calculate the average value, I of average is equals to, so for a half-wave rectified output, the total time period is what? 2 pi. Okay. But the thing is, we will get the output from 0 to pi only, and we will get 0 from pi to 2 pi. Okay. Or another scenario may arise, we will not get any output from 0 to pi, and we will get output from pi to 2 pi. So the total time period will be 1 by 2 pi. But the thing is, we will only do the integration to find the value of current from either 0 to pi or either from pi to 2 pi. So I am considering here that we are getting the positive half cycle in the half-wave rectified output and we won't be getting the negative half cycle. So to perform the calculation, I am considering time period from 0 to pi. Okay, 0 to pi. I am representing this sinusoidal waveform as Im sine of alpha. Okay, Im is the peak amplitude in the positive half cycle and minus Im is the peak amplitude in the negative half cycle. So we will perform the integration from 1 by 2 pi, integration from 0 to 2 pi, Im of sine of alpha, okay, d alpha, right. So if we proceed with the calculation, 1 by 2 pi, we will get Im here. If we take Im common from here, Im by 2 pi, then sine alpha, integration of sine alpha is minus of cos alpha. And the limit are from 0 to pi. So if we do the calculation, we will get Im by pi. Okay. So this is the, we can say the average value of current for a half-wave rectified output. Now, if we want to calculate the RMS value, so the RMS value, the calculation will be similar. But the thing is, the total time period will remain the same. It is from 1 by 2 pi. It is 2 pi. The total time period is 2 pi. We will do the integration from 0 to pi. And here, instead of Im sin alpha d alpha, we will perform the integration of Im square sin square alpha d alpha. And this entire calculation will be within a root. Okay. 1 by 2. I am representing the root as 1 by 2. So here, if we do the calculation, we will get Im divided by 2 pi 0 to pi Im square. We will represent sin square alpha as 1 minus cos 2 alpha divided by 2 of d alpha. Okay. To the power 1 by 2. And if we do the calculation, we will be getting Im by 2. Okay. So now we know the value of the, we can see here. Now we know the value of the DC. We know I of DC. And we also know I of RMS here. We also know I of RMS here. So we will just put the values here. We will be getting, if we put these two values here, we will be getting a ripple factor of 1.21. Okay. So this is the answer of the question, ripple factor of half wave rectifier. And now, if we want to find the efficiency of a full wave rectifier, the efficiency can be found in a simple manner. So let us perform the efficiency here. Okay. Okay. Yeah. So let us perform the efficiency here. So in a full wave rectifier, okay, the efficiency, this is equals to, I am representing efficiency by eta. Okay, this is the symbol of efficiency. So this is equals to P of DC divided by P of AC. Okay, and we know E is equals to I square R. Okay, so P of DC, this is the output power. Okay, so if we consider that at the output there is a load resistance which is RL, so P of DC, this is equals to I DC square into RL, as P is equal to I square R. Okay, and P of AC, okay, P of AC, this is equals to I RMS square, because the input waveform is AC. So we will be writing I of RMS square into RL plus RF. Okay, then this RF is just a series resistance which is connected in the full wave rectifier to limit the current. Okay, so we will find the values of IDC and IRMS and we will just put them here to get the total calculation. Now in the half wave rectifier, we have seen the total time period was 2 pi. Okay, the total time period was 2 pi and the output was somewhat like this if we consider the positive half cycle only. But in the full wave rectifier, for the positive half cycle, we will get this output, and as well as for the negative half cycle, we will get this output. Okay, so we will get both the outputs at the half wave rectifier output. So this is for the negative half cycle and this is for the positive half cycle. Okay, so this period is from 0 to pi to 2 pi. So as we can see, this cycle is just repeating every pi distance. This cycle is from 0 to pi, this cycle is from pi to 2 pi. Similarly, we will get again from 2 pi to 3 pi like this. So the time period is pi. So here we will just do the integration from the total time period is pi, because in the half wave rectified output, we will get either the positive half cycle or the negative half cycle. So the total time period was from 0 to 2 pi. But here we can see that the cycles just repeat every pi interval, every interval of pi. So from 0 to pi we are getting a cycle, from pi to 2 pi we are getting a cycle, and from 2 pi to 3 pi we are getting a cycle. So we will consider the total time period as pi and we will perform the integration from 0 to pi for this cycle only. Okay, so it will be like Im sin alpha d alpha. So this will be equal to Im by pi minus sin alpha integration is minus cos alpha 0 to pi. So it will be equal to 2 of Im divided by pi. And similarly, I of RMS, this will be equal to 1 by pi 0 to pi Im square sin square alpha d alpha to the power half, and this will give us a value of Im by root So if we put these values here, IDC square is equal to I average square, which will be equal to 4 IM square divided by pi square, and I RMS square is equal to IM square divided by 2 into RL plus RF. Okay. So this will give us one thing I will do. I will just take I will just take RL common from here. So if we take RL common from here, we will be getting RL into 1 plus RF by RL, and this RL and this RL will cancel out each other. So we will be getting 0.812 divided by this IM square will cancel out each other. So after performing this calculation, we will be getting 0.812 divided by 1 plus RF divided by RL. Okay. So we will just consider there is this RF, this is equals to 0, no series resistance is connected. So if RF equals to 0, the output will be 0.812, and if you multiply it by 100, the efficiency will be 81.2%. So this is the required efficiency of our full wave rectifier. Okay, so this is the answer. Thank you.